Morning, ladies and gentlemen. Happy Halloween. I hope the weather cooperates for you this evening. Let's get all the rain over with during the day. No real announcements. You know what you're supposed to do. There's a project checkpoint soon, very soon. And there's a little homework as usual. Basically, this is just a normal week. Any administrative questions before we get on to the main business of the next couple of weeks? All right. So we've developed quite a lot of technique, and last week was perhaps the most mathy week of the course, where we set up some theory about how, in particular, sample means behave, but random quantities, what you expect them to be, and especially a quantification of the plus or minus number. And what we'll take away from that is some understanding of distributions that follow bell-shaped curves, why some distributions follow bell-shaped curves, standard deviations, the measure of spread about the mean, and crucially today, conversion to standard units. Any variable, any distribution, any shape at all, you can treat the mean as the origin and the unit of measurements as SDs. So you go, 0 plus minus 1 SDs plus minus 2 SDs plus minus 3 SDs, and then you set a number line down. And on that scale, no matter what the distribution, Chebyshev tells you that your values are going to be pretty much in the minus 4 to 4 range, maybe minus 5 to 5. The good thing about this, as you will see today, once we start dealing with relationships between variables that are in different units, so somebody's age, their dosage and their machine for their medication, their height, weight, blood pressure, and so on, all of these are in different units. But you can compare distributions and you can compare scatter plots by measuring everything in standard units. That's very helpful. So what we're going to be doing today is one of the main responsibilities of a data scientist, which is to make predictions about the future based on data at hand. And this week we will focus on a very simple goal, which is we know for a bunch of individuals, we know the value of one variable. We're trying to estimate another. Okay? So, for example, we know the person's blood pressure, and we are trying to figure out how they're going to respond to a particular treatment, just one-on-one. And before we do anything new, I would like to take a moment to remind you that we've actually done this already. Any memories of that picture? That was Sir Francis Galton's data on heights of parents and their adult children. He was the first person to formalize making predictions in the way that has become absolutely standard in data science and every other field of application. So I'll just remind you about his data. He had about 900-something adults, and the variable that he had was on on the vertical axis, the black points represent the height of the adult. And on the horizontal, there's a kind of weighted average of the parents' heights. And what he was trying to do, he was interested in how physical characteristics are passed down from one generation to the other. And he was therefore interested in saying, if I know the heights of a parents, then how can I predict the height of the child? And so he had 900-something data points. For each point, there was an adult and their average height of their parents. So, for example, this person was themselves 60 inches tall, and their mid-parent height, the average height of their parents, was somewhere in just between 71 and 72. And so you can see the dots are all over the place. As you remember, that is called a scatter plot. The idea is now there is a new couple, and you want to estimate the height, you want to predict the height of their child, their adult height of their child. Can somebody remind me what was the approach that we took? So supposing the new couple has a mid-parent height of just there. Then what? Yes?
We average the nearby data points.
we average the nearby data points. Thank you. So what we said was if the new couple is somewhere here, their average height, then we can kind of forget about all of this. They are like these points. When you plot their child's height, it's going to be somewhere in this range. That is a reasonable assumption to make. So we said we are going to average the black points, the heights of the black points, for the mid-parent height close to our new value. And in our analysis, we just defined close to be something. I think we just defined it to be close to be within half an inch. Right? And so I'm going to walk up the line 68 here. This dot right here, the height of that dot is the average height of the children whose parents had a mid-parent height of around 68 inches. Yep. We didn't take exactly 68 inches because there's probably not many at that at exactly 68. We took a round. It's sort of called nearest neighbor estimation. So we did that for every single one of the mid-parent heights, and we got this sort of what we call the graph of averages going along there. And the business of this week will be to formalize that, to see if we can come up with that in some way. Sure looks like a straight line. We should be able to identify that straight line. And then, crucially, see how good that estimate is. And for this, I'd like you to look at this point right here. If somebody has a mid-parent height of just about here, what's our prediction? Is it there? It's not. It's here. Yeah, so we're over-predicting. And for this point, the error in prediction is going to be a large negative value. Error is actual minus prediction. Yep. So for that point, it's going to be a large negative value. For this point here, negative or positive? Positive. For every point above the line, you have positive errors. For every point below the line, you have negative errors. Take a look at that graph. Think about what you know. If I average out the errors, what do you think I'm going to get? 0. Yeah, pretty close. And we will see that if you take a particular line, it's exactly 0. That is parallel to the result that we've seen before, that if you have a list of numbers and you take the deviations from the average, then those deviations, the plus and minus, exactly cancel each other out. So a lot of what you're going to see this week is going to be the two-dimensional analog of what we saw last week. Right? And I hope that it will, therefore, be not surprising at all. Okay. And so what we're going to do is we're going to measure how good our estimate is, and for that we will need a sense of the size of these errors. And because the errors cancel each other out, if we keep the signs, we are going to do what to the errors? We're going to square them, et cetera, et cetera, et cetera. We're just going to go through one more time what we've done already. And the nice thing is that because of the mathematics, there are some very powerful results that make the eventual calculations quite straightforward. So what I would like to do is I'd like to start with a recap of this particular calculation and then start to quantify some things that we can see. So I will get to my notebook here. Okay, so these are the data. The table was much larger. You had, for every child, you had birth order, you had each of the two parents' heights, you had an index for the family, and so on. We've just narrowed it down to just the part that we need. All heights are in inches. There's the scatter diagram. And so that there are no mysteries, I just want to remind you of the function that we wrote to do our prediction, to get those gold dots in the center. We said that given any mid-parent height, we would look at the heights where the mid-parent heights are between the given height plus or minus 0.5. Do you want to take a look at that? That line there, close points is a what? Close points up there in the code, on the code. The close points is a number, an array, a table, a what? It is a table. It is derived from the table heights. You're doing .where, that returns a table to you. And it selects exactly the rows where you have mid-parent heights in the range given plus minus 0.05. And then what does this function return? Does it return a table, an array, a number, what? A number. It's returning a mean. Yep. And it's returning the mean of the array of children's heights for your new table that you have calculated. Questions? All right, so we are going to do this prediction, and notice it chugs. Why does it chug? It's doing something it is making a table each time, but it has 934 mid-parent heights, for each of which it is selecting the rows that are close and it is making a prediction. And so, it takes a little bit, and it's done. And that's the scatter diagram that was on the first slide. And so the reason for showing you this is first to remind you of what we did to get to here, and to point out that there was no mystery. We didn't use any formula. We didn't use anything. We didn't use the fact that this scatter diagram was roughly linear. In fact, in the homework that you did directly after we did this lecture, you had a scatter diagram that was kind of wavy. And you did this method of estimation, and your pattern of gold dots was kind of wavy. So you can take this as a way of making predictions given any shape of scatter diagram. The one thing that's a little bit of an issue here is we defined close to be plus minus 0.5. Yep, but we could have taken plus minus, 1, yes, or 0.25 or something, and I'm just, just for fun, I'm just going to do it. So if we do 0.25, so close to be quite a bit closer, define the function again, and let that thing chug again. Can you predict what the gold dots are going to look like? Are they going to look the same? Are they going to look more wiggly, less wiggly? What? Instantly, I got both. You've now narrowed down your interval. Yep. If you are trying to make a decision and you don't know how, go to the extreme. Right? Supposing you had taken close to mean plus minus 10 inches. Then what would you have got? I don't know. Everybody's going like that, but let's just think about that. 68, right? If I had defined close to be plus minus 10 inches, I would have taken all the points that go from 58 to 78 and taken their average. Yes? 72, I would have gone from 62 to 82, and I would have taken their average. Yes? What would I have got each time? The average of every single point, basically. Yes, I would have ended up getting exactly the same thing. Very smooth. The bigger the interval, the smoother your graph is, the less information you have. So now we've made the interval small. What do you think is going to happen? Let's see. It's done now. So it wiggles a bit more. Not a ton more, but it wiggles a bit more, near 68, 67. There's a bit of wiggling. And so then now there's this issue of exactly what is close. How do I make that decision? And so if you can avoid making that decision, that sounds like a good thing to do. Somewhere there is a line. And Galton's genius was recognizing that there is a line. And once you know, and from high school when you draw an Excel scatter plot, it gives you a best fit line, you just go, well, obviously there's a line. But for all of those centuries, nobody saw the line. Right? So once somebody points it out to you, it's obvious. But before that, it takes somebody with a bit of perception to notice. So that was his contribution. What we're going to do is identify where that line is and how to use it, how to come up with it, how to calculate it, how to use it. And so we're going to have to start now quantifying some things. And one of the things we're going to quantify, actually let me go to my slides. is the relation between two variables. You know already, what is association? Any relation whatsoever between two variables, any relation. A trend is when you see the scatter plot either in general going up or in general going down. And so you will remember positive and negative association corresponding to upwards trend and downwards trend. These are all old terms. I just want to bring them back because we're going to use them quite a lot today. A pattern is any shape to your scatter diagram. So if it's wavy or if it's linear and so on. And as we see lots of scatter diagrams, you'll start spotting patterns. Pretty much everything has a pattern unless it's a great big blotch. And we're going to see some great big blotches today as well. Sometimes they're actually highly desirable. So what we're going to do, as always, is we're going to visualize and then we are going to quantify. So just so that we can move away from heights and mothers and babies and so on, because we're really tired of those, here's a data set on every single hybrid car from when they started making hybrid cars to about 2013. There's 153 of them, and you have data on what the vehicle is, the year it was manufactured, manufacturer's suggested retail price, acceleration, that's kilometers per hours per second, but never mind, it's just how fast it rooms. Mileage, miles per gallon, and the class of the car, what kind of car it was. And in case you are interested, No. These are in 2013 dollars. So that's the Lexus. What are these? Active hybrid? Those are BMWs. So there are these, and then there are the Honda Civic, modest compared to the others. Okay, so there's 153 of these. And what we're going to do today is just do some descriptive analysis of relations between variables. Some language, this is a price versus mileage. When you say something versus something else, the first one is on the vertical. Okay. So this is a price versus mileage. Look at that. Big mileage, 50 miles per gallon, that's supposed to be a good thing. That is supposed to be a good thing, but it is not commanding a lot of retail price, is it? People ain't paying for that. Now, note, please, that this is among the class of hybrid cars to start with, right? But among them, people aren't paying for the one that have the best mileage. What are they paying for? I think you can guess. They're paying for vroom, vroom, vroom. 0 to 100 in 5 seconds, or whatever it is. That's what they're paying for. And it's just happens to be a fact about cars that the ones that accelerate very fast tend not to be the ones that have the best mileage. And that's what you're seeing there. And so this is just, recapping that when you look at multiple variables, then, just think about the variables before you make, especially if you make any causal connection and so on. I have rather blithely said people are paying for acceleration. That is true by this graph. People did pay more for the cars that accelerate more. Whether the acceleration was the reason they paid more is something that I can't conclude based on the scatter diagram, right? But I can see the positive association. Okay, there's something else I want you to look at here. This scatter diagram is nonlinear. There's a clear curve. This one is more linear. It just sort of goes up sort of straight. And so when you look at scatter diagrams, scatter plots, you're going to have some decisions to make about whether you think it's linear. And somebody can argue and say, well, it's kind of not linear. There's a bit of a curve here. Yes, certainly there can be doubts in visual perception. But one of the things to be aware of is when you see a curve like that, look at your data. These data are actually not just one entire data set, but there are compact cars, there are minivans, there are this, there's that. Possibly some of those behave differently from others. And so potentially you have some of those in a clutch and the other ones in another clutch. It's well worth sorting them out, sorting out your scatter plot by the different types that you have. And so what did I do? I took the SUVs, and there were about 40 of them. And for the SUV, the 40 SUVs, the acceleration versus price looks like this. For all, it looks like that, not that different. Yeah. The other one, however, price versus mileage, this is rather linear, whereas if you look at the whole lot combined, that's noticeably nonlinear. Now, if you're going to understand the relation between two variables, the first one to start with is linear. If you can't understand linear, you have no hope of understanding anything else. So today, for this week, we're going to focus on linear. Okay? And then hopefully we'll be able to show that you can use what you understand about linear to develop nonlinear predictions as well. Okay, so I will now start getting a little more technical, but for what we have said up to this point, are there any questions? So far, so good? So I want you to notice something. We've been saying this one's nonlinear, this one's linear, and what have you been using in your head to make those decisions? I know what I'm using. I'm just looking at this shape. I have totally ignored these numbers and these numbers. Did you look at these numbers, or did you just look at the shape? You just looked at the shape. So did I. Right? And we did that for this too. So what we're noticing is that these numbers actually don't affect whether we think the graph is linear or nonlinear. So the units don't matter. And so we are going to measure in what? We're going to measure in standard units. Right? Then we can put both graphs on the same axes and actually be able to compare better. So I will recall standard units now. You remember that standard units, you take a number, you find its difference from the mean, and then you compare that to a standard deviation. We had written this function before. It takes an array of numbers and converts the entire array to standard units. So it figures out the mean of the array, the SD of array, and then converts each single one to standard units. This is a function that we had written. It's not a built-in. So I define that. And what I'm going to do now is I am going to create a plot of the SUV price versus mileage with variables measured in standard units. So first we're going to look at the plot, and then we're going to look at the code. All right, so this is the plot we're looking at. Standard units MPG on this side, standard unit MSRP on this side. Keep that plot in your head and compare with this one, which was in the original units. This is in miles per gallon and dollars. And here is the same plot in standard units. Yep. All that's happened is physically one of them is smaller, but it's the exact same plot. For code, what I did was we created a new table. Okay, so I'm actually going to read this one in gory detail so that everyone's clear about exactly what's happened. Starting from the left, table up to here, table with empty parentheses. What does that create? An empty table, right? You start with an empty table, and then you add to that columns, plural, because I'm going to add two columns. So the first one, this one is the label of the column. I'm going to call it miles per gallon in standard units. Now, what is happening here? What is this standard units right here? It is the name of a function. It is the function that we defined. The definition is just up there. That function operates on what kind of object? On an array. So if I'm going to call standard units, I better give it an array. So SUV is what? SUV is a table. I can't give it the table, so I extract an array by doing the obvious thing, which is the column. Yep. Which column? Miles per gallon. That is the one I'm trying to convert to standard units. Okay, so I will let you look what is going on here. Yeah. Take a look at that. The construction of the table, and then we do the same thing over for the price, and then we do a scatter diagram, column 0 on the horizontal axis, column 1 on the vertical. Column 0 is miles per gallon, so that'll be on the horizontal, 1 is price, and that'll be on the vertical. That's as far as I'd like you to understand. This is just me fixing the units so that you go plus or minus 3 SDs on either side for both variables. And the reason I am doing this in detail is I have gone through some of your midterms, and I am seeing the, what should I say, rather impressionistic coding that's being written down. So I just want to make sure that this thing is nailed down, that we understand what each piece represents, because it does matter. Okay. And then we'll play the same game with the other one. This is price versus acceleration. And now, what's the benefit of having done this? So I had that one and this one in the original units. And, this is kind of linear and that's kind of linear, but you really can't compare the two because the units are different. Now you have this plot here and that one that are in exactly the same units, plus minus 3 on either side, both axes. You can compare them, and if you take a look, and I'm sorry I didn't do them side by side, is if you look at this one, the one going up, and you look at this one, the one coming down, I think the one coming down has a tighter linear relation than the one going up. So keep this one in your head. I just see more fuzz. This one's tighter. This one's more all over the place. And so what would be nice to do is to have a measure of tighter versus all over the place. If you can just quantify and not have to do it just by eye. And so that's what we're going to do now. And so there's a number which has a very impressive name. It's called the correlation coefficient, and nobody can say it, so everybody says R. This measures linear association. It's based on standard units, which is exactly what you'd want it to be. It is a number between -1 and +1. The maximum, R equals -1, the scatter diagram is perfect straight line sloping upwards. The minimum, R equals -1, scatter diagram is a perfect straight line sloping downwards. Notice that the sign is going to be the sign of the association, positive or negative. +1 and -1 are the extremes. R equals 0, we say the variables are uncorrelated. Please note down somewhere, preferably in your own blood. Uncorrelated means no linear association. It does not mean no association. That is a very important thing to remember, especially in an era where people in normal English just use the word uncorrelated to mean unrelated. That extra syllable actually makes your case weaker. Unrelated is a lot stronger than uncorrelated. Right? So please, when you go out of this class, don't say things like those two variables aren't correlated at all, unless you really want to say those two variables don't have a scatter diagram that looks like a straight line. Right? If you want to say those two variables aren't related at all, please just say those two variables aren't related at all. That is exactly what you want to say, and that's what you'll be right. All right? So I have wondered for a long time why people keep throwing in this extra syllable and therefore mucking up what they're trying to say. I think it just makes you sound more educated, the more syllables you have. I don't know. But you know, if you're going to be educated, then know what you're talking about. Okay. So I haven't described to you at all how to calculate the number, but I just want you to, what we're going to do is we're going to just play with the number for a bit. This is a function that we wrote, and what it does is it generates a scatter diagram with R as entered here, or pretty close. It's a simulation, so you don't get exactly 0.9, but you get very, very close. There's, I think, 1,000 points in that scatter diagram. Okay. So what I'd like you to do is I would like you to give me different values of R, and we're going to rerun this cell. 0.2, thank you, I like that. Yep. And while you have 0.2, you take a look at that. That's kind of very blobby, right? It's very hard to see any linearity at all. And if I just do 0, so this is 0.2, remember? If I just do 0, I don't know. I mean, you have to take a ruler and see where those points are lying. And this is an extremely important issue because our points may be samples from a larger population or, derived randomly somehow. And possibly we will look at something and think that there is a positive correlation, whereas in fact there isn't. And you can see that it's entirely possible to make that mistake. Right? It is hard to tell R of 0.2 versus R of 0, even with 1,000 points on the scale. So we're going to spend some time working out how do you distinguish whether you actually have a correlation or not. For today, the values of R are going to be quite a bit larger. I think it's a good idea to look at some negative number. Negative number, things slope down, just to check that this thing is doing what it ought to do. If I do -1, what should I get? I should get a line. If I remove the minus, I should also get a line. Okay. Yep. So what R is doing, the sign of R gives you the direction of the trend, and then the magnitude of R. So let me compare once again, 0.9. Take a look at that. That's kind of skinny about the straight line versus 0.6 is more fuzzy. So R is, what you can see is it's measuring the degree of clustering about the straight line. Okay. And so now what I would like to do is just go through the calculation. The reason for going through the calculation is that you can see some of the properties. And then we're going to start using this thing. So I'm going to take a simple little, at this point the code starts to matter less because it's rather straightforward. So I'm going to take a very simple set of 6 XY points and show you the scatter diagram. Right, ladies and gentlemen, if I calculate the correlation for this, is the answer going to be 0, positive, or negative? It's going to be positive. That thing is in general sloping up. So if it's going to be positive, is it going to be +1? It is not going to be +1. It's not a straight line. So you expect some number in the 0 to 1 range. Okay. So here's how you calculate. The first thing you do, since this measure is based on standard units, is you compute both variables in standard units using our handy standard units function. Right? Okay. Now you've got both variables in standard units, and just take this as an algorithm for me for the next couple of moments. Take each pair of standard units and multiply. So this 0.9498 is minus 0.6488 times minus 1.46, etc. So each of these is the product of the previous two, which is just an array operation. You multiply one array by the other array. Okay? To get R, you take the average of the products. And your answer is 0.61 something, so roughly 0.62, and you had told me by looking at the picture that it's going to be positive and it's not going to be +1, what you get is 0.62. So R is the average of the products of standard units, and once again, that's a formula, and you read it backwards. Step 1, calculate the standard units. Step 2, multiply. Step 3, take the average. You've got R. Now, there is a little issue as to why this gives you a measure of the degree of linear relationship. That takes a little bit of mathematics. What I would like to do is just go over this calculation shows you some of the properties. I'd like to go over those quickly. Okay, so for the definition, you take both variables in standard units, you multiply, you take the average. And we have seen, though we don't know quite why, it measures how clustered the scatter is around a straight line. Okay, so I would like to take a look at some properties of this thing. Okay. It's based on standard units, therefore it doesn't matter what units the variables were measured in. Therefore, you can say the correlation between height and weight, you don't have to worry about whether height was measured in inches or centimeters. So it does not depend on units, it's a pure number. Second, this product, what do negative standard units mean for the value? Negative standard units mean what? That minus. It's below average. Yep. So the x was below average, the y was below average as well. Notice that the product then is going to be plus. So now if you have positive association, in general, above average values of x tend to go with above average values of y. So positive standard units tend to go together. Also, below standard units of x go with below standard units of y. So the negative standard units tend to go together. So when you multiply, in general, you get a plus. I have only one point here where x was above average and y was below. I think all the rest of them, the standard units have the same sign. Yep? And that multiplication ends up giving you the right sign. There's the Cauchy-Schwarz inequality of mathematics says you're going to get a number between -1 and +1. We won't go there. Now we're going to want to calculate correlations over and over again. And so what I've done is here's another one of our own definitions. The correlation as a function, T is a table. X and Y are the two columns. And it returns the correlation. So what does it have to do? Well, it needs to convert stuff to standard units. So it extracts the column X, converts it to standard units, extracts the column Y, that's an array, converts that to standard units, multiplies, and takes the mean. Yes? That function computes the correlation between column X and column Y of your table, and I just want to make sure that it works. Okay, so we're saying for the SUVs, between mileage and price, we had a negative correlation of 2/3, where that's this. Does that look good? Minus 2/3, you actually have no idea whether that should be 2/3 or minus 0.5 or what. But minus looks good. All right. It's very hard to see correlations by eye. Okay, now the positive acceleration versus price, we get about 0.5, so it's 0.5 versus about 0.7, and that now quantifies what we had observed, that the acceleration and price picture is more fuzzy than the mileage and price picture, because this is minus 0.7 roughly versus plus 0.5. Right, so the plus 0.5 is telling you less clustering about the line than minus 0.7. Yes? Okay. X and Y here are labels of columns of T. So if it will help you to remember, I will just change the name here. Label X, label Y, and then I have to stick them back in here. And let me make sure that I didn't mess anything up there. No, it's fine. Okay, So there is one thing that I would like you to observe. That's my scatter diagram, X versus Y. What happens if you switch the variables? If I switch the variables, I draw Y first and then X, is that scatter diagram going to slope down? Should we see? This has Y along here and X along there. That has X along here and Y along there. Switching axes corresponds to what? You are flipping. What are you flipping around? The X equals Y line, right? It is important to note that which one you put on which axis doesn't change the trend. And you should also be able to see without any calculation at all that the degree of clustering here is precisely the same as the degree of clustering here about a straight line. You haven't done anything to the linearity. And algebraically, the measure is based on a product. Which one you're calling X and which one you're calling Y shouldn't matter. Right? X times Y is the same as Y times X. And so it is important to note that our correlation, when we specify the columns X followed by Y, is exactly the same as the correlation when we specify Y followed by X. And so in practical terms, what does this mean? We've already said you can talk about the correlation between height and weight. You don't have to worry about units of measurement. But now you also don't have to worry whether it's the correlation between weight and height. Right? You just have the correlation between two variables, regardless of how you've measured them. And that's quite handy to have. All right. And so that is the calculation. And let me just see if I have forgotten to do something. So it's a pure number. It's not affected by changing units. Not affected by switching the horizontal and vertical axes. Okay. This thing gets used a lot. A lot. And so we want to have some basics down. You know some of them. The first one is, if you've seen a correlation, you haven't necessarily seen causation. We have a silly example from weeks ago. If you look at shoe size and reading ability among K through 12 children, that has a positive correlation. That is not causation. You agree? What's the confounding variable? Age. Yeah, older children read better. Okay? So association is not causation. You've known that for quite some time. For correlation in particular, there is one thing to watch out for. Okay, take a look at that scatter diagram. Are you seeing an association? You should be able to answer with confidence. Are you seeing an association? Yes. In fact, Y is equal to X squared. That's about as sharp an association as you can get. All right, are you seeing a linear association? You are not, and indeed, if you run correlation, you will get 0. These two variables are uncorrelated. However, they are very closely related. So once again, the point is, uncorrelated does not mean not related. No linear relation, but very strong nonlinear relation. So if you're going to use R, please remember our rule that I had in bold in one of the slides. First visualize, then quantify. Right? If you draw the scatter diagram first, and it's wavy like a snake, you shouldn't be calculating R. Okay, so nonlinearity is a problem. Here's something that's interesting that people don't always anticipate. Okay, there's a scatter diagram. Correlation, please. 4 points on that diagram. What's R? +1. It's a perfect straight line sloping upwards. Yep? Okay, I'm going to throw in one outlier. Same 4 points. I throw in this one outlier. Is correlation still +1? Not +1. Let me show you what the correlation is. You ready? 0. That one outlier took your correlation from +1 to 0. Outliers have a massive effect. So if you have a scatter diagram and much of it is here, but then there are 2 points up there, and we had a scatter diagram like that. Do you remember the actors and the average money that their movies made? And there was Mr. C3PO who was all the way up there. It would totally mess up the correlation there. Right? So you probably shouldn't be calculating correlation, or you should be trying to understand why that person is so different. But outliers have a huge effect. Don't just blithely compute R. How will you know there's an outlier? Because you will have visualized first. Yes? So there's always this desire to exclude the outlier. If you've got a really good story for why you want to study only the rest of the population, and every time your subsequent analyses remind the reader that we left out these 3 people, then you're fine. But blithely leaving them out, I had somebody from a well-known university call me up and say, can I leave out the outlier and say that because this outlier isn't fitting my correlation? No, actually. You need to look at that outlier and work out. If you're lucky, it's just a measurement error, but with Mr. C3PO, Anthony Daniels, it wasn't measurement error. He just picked his movies. And so you have to say, well, why do I care about all the actors except this one? Because if I were an actor, I would be very interested in him. Right? I just need to work in the X-Men franchise. That's it. I'm not going to do any other work. Okay. So outliers matter. And finally, I want to show you something that is perhaps slightly less obvious. These are the SAT scores. The SAT has all changed this year, right? But I think when you took it, it was still critical reading, writing, and the other thing, whatever that was called. Okay. Yeah. And so there was a combined score out of, 2,400? All right. So here are data for 2014, these every single state and DC, average scores. Okay? And what we're going to look at is the scatter diagram of critical reading versus math. There is 1 point corresponding to every state plus 1 point for DC. Take a look at that scatter diagram. That's as close to a straight line as any genuine scatter diagram that wasn't made up by me gets. Okay? And in fact, if you calculate the correlation, it's about 0.985. And it is really tempting to look at that and go, wow, the scores are really correlated. Like if I know somebody's math score, I almost exactly know their reading score, but you know that's nonsense. That just can't be. So when you see a correlation like this and you're beginning to get really excited about the R, go back to the variables and ask, okay, so they're measuring critical reading and math on whom? What is that? Is that a person? That's a state. Key question. Do states take the SAT? Answer, they do not. Signal problem. Right? So what you have done for this state is this state had lots of students. They had critical reading scores that were all over the place and math scores that were all over the place. This just bunches all of them into their average. Yes? All of the students in that state have been lumped into one person holding the flag of the state. You have artificially, therefore, removed the variability. You have artificially, therefore, increased clustering. So that 0.984, yes, it's very high, but it doesn't mean anything. It is true that if I tell you the average critical reading score in a state, then you can, with high precision, give me back the average math score in that state. If that is the game you want to play, you can play it very well. But people are really interested in average, other than the state governments themselves, are really interested in the connection between averages of states. People are interested in averages of people. Yep? And so if you had a point for every student who took the test, would R be equals 0.985, less than 0.985, greater than 0.985? Less, the picture would be much more fuzzy. Because each state, the point for each state would be replaced by a fuzzball. Yes, and you'd have 52 of those. All okay? So these are called ecological correlations. When you see correlations based on aggregates, or averaging, watch out. Always ask yourself, before you start getting into the numbers, on whom did they measure? And there is a wonderful example of this that I want you to go look up. Got to go look this up. There's a reference in the textbook. In the New England Journal of Medicine, a scatter diagram. There is 1 point for each country. On the horizontal axis is average chocolate consumption per capita. On the vertical axis is Nobel Prizes. Switzerland's way up there. R is 0.791. Notice the tiny p-value. Somebody did a hypothesis test. Okay, conclusion being more chocolate, more Nobel Prizes. Go eat chocolate. Okay, it's Halloween. I had to show you that. Go eat chocolate. I'll see you later.